Hi everyone, I'm Dr. Andrew Tehemi Tiowa of the Department of Chemistry, Benue State University, Makurdi, Nigeria. My project is on salt-induced edible non-spherical Pickering emulsion droplets. An emulsion is a mixture of two immiscible liquids, for instance oil and water, in which one of the liquids is dispersed as droplets in the bulk of the other one. Emulsions are made stable by adding either surfactants or small solid particles, otherwise known as colloidal particles, to the emulsion during preparation. As can be seen here for the case of particle stabilized emulsion. So here is oil, here is water, the colloidal particles on the surface there. If this mixture is shared vigorously, emulsions with either spherical droplets are going to form, or those with non-spherical droplets will form, depending on the particle type as well as the sort of equipment used. Emulsions with spherical droplets are very easy to prepare, 100% or 99%. You mix the ingredients together, you're likely to get emulsions with spherical droplets. The story is rather different when it comes to emulsions with non-spherical droplets. In that case, either exotic particles or equipment are required. So here we report a method for preparing emulsions with non-spherical oil droplets in which exotic particles and our equipment is not required. Basically, what we did was we took an aqueous solution of sodium chloride. We added calcium carbonate particles, either the cube-shaped ones or the rod-shaped ones. We introduced oil, vegetable oil in this case, milk oil, sunflower oil, or olive oil. We shared the mixture vigorously using an ultra-trax homogenizer. We obtained emulsions. We characterized the emulsions using optical microscopy, scanning electron microscopy. We also investigated the stability of the emulsions with respect to creaming and coalescence. What we observed was, in the absence of added salt, both the rod-shaped and cube-shaped calcium carbonate particles formed emulsions that had spherical oil droplets. So this is a visual appearance of a glass vial containing vegetable oil and water emulsions in which the droplets are spherical. Here is the scanning electron microscope image of the emulsion system showing the spherical oil droplets, and this is a zoom-in version of the surface of the oil droplet. Here is a sketch of a dissection of the oil droplet coated with the calcium carbonate particles, showing the cube-shaped particles on the surface of the oil droplet and the oil as well as water there. This can also be seen for the case of the rod-shaped calcium carbonate particles, as shown here for the scanning electron microscope image. And if we dissect this, we find that the rod-shaped calcium carbonate particles absorb on the droplet surfaces. This is the oil droplet, and that's water. Furthermore, when salt was added into the emulsion system prior to emulsification, we observed that non-spherical emulsion droplets were formed in systems containing the cube-shaped calcium carbonate particles, but not the rod-shaped calcium carbonate particles, irrespective of the amount of salt added. Here is a glass vial containing an emulsion system that has non-spherical oil droplets. This is an optical microscope of the emulsion showing both the non-spherical oil droplets as well as few spherical ones. This emulsion with non-spherical oil droplets were stable for more than 3 years in terms of creaming and coalescence, although they release a small fraction of oil and water. So for the case of creaming, we observe that the fraction of water resolved in 3 years increases with increasing salt concentration, presumably because the electrostatic repulsion between the particles decreases as salt concentration was added, giving rise to a case where the particles on the surface of the oil droplets allowed for flocculation and aggregation, and of course flux rise faster than the individual droplets. So creaming was enhanced as the concentration of salt increases. For coalescence, we measure the fraction of oil resolved in 3 years with respect to the concentration of sodium chloride. And we saw the same trend. The fraction of oil resolved increases with increasing salt, also for the same reason of decrease in electrostatic repulsion between the droplets as salt concentration increases, so that poorly coated oil droplets became prone to coalescence, leading to the fraction of oil we've observed in this system. This work was done at the Department of Chemistry, Benue State University in Nigeria, and it was supported by the Tertiary Education Trust Fund of Nigeria. It was published in the Journal of Dispersion Science and Technology, and if you scan the QR code, you will have access to the full paper, which I encourage you to do. The corresponding author can be contacted via the email address given here or via Twitter. Thanks for watching. This is how to make a virtual poster presentation. And I invite you to subscribe to this channel for tips on scientific writing, including scientific papers, posters, and oral presentations, research and book proposals. We're also available for one-on-one and group coaching on scientific writing. For more details, you can contact Dr. Andrew Tiokwa via the email address displayed on the screen. Meanwhile, you can find tips on scientific writing in a book entitled A Practical Guide to Scientific Writing in Chemistry. Scientific papers, scientific posters, oral presentations, research grants, and book proposals, published by Taylor and Francis for Dr. Andrew Tiokwa. Bye.